Okay, so let's start, but I just wanted to go around the room and just see the status on kind of your project ideas. So, what are you guys leaning towards? I know you were talking about some things last time with me. Okay. I think to force the decision, so I think what I would like is that everyone to send me their project idea by this Thursday, that's day after tomorrow. Okay. I know you had sent me some email, so again, are you two going to be pairing up? Okay. Uh, what project are you leaning towards? Yeah, start with you. Hmm? Okay. End of the week. So do you think I can get something from you on Friday? But what are you leaning towards? Like, have you discussed anything? Have you discussed anything? Okay. 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 We are in which week now? Third, fourth? Which? Fourth. Okay. So I think it's high time that we finalize the project. What, what about you? What project? Actually, does it? Does the Intel Galileo consume more energy than Arduino? It does? Okay. Okay, maybe after the class, if you can describe to me a little bit more in depth. Okay, and what are you planning to do? You are just auditing. Okay, so you're not planning to do anything. Okay, and you have spoken with me. So okay, uh, so uh, last time around we started looking into power management, and I introduced this kind of broadly kind of several categories of things that can be done. One was kind of this design time scaling, select the right degree of parallelism combined with voltages and all. And then we were moving towards more dynamic techniques. And very broadly, there are dynamic techniques which cater to shutting things down. And there are dynamic techniques which cater to using some sort of performance power knob. And so, for example, in case of a processor, it's voltage and frequency being controlled. So let's look at the shutdown-based mechanism. Um, uh, right now I'm going to describe things in a more generic fashion, and then the next slide set will go into how things are done in one particular OS, and that's Linux. So that's the slide set that I'm handing out. So essentially what happens is the following, that you can think of hardware as kind of like a service provider, and there are tasks coming which need the service of that hardware, except that these tasks come and go. So there are times at which the services are not needed. So somehow you need to arrange for this hardware to be turned on and off in response to that. So that's that. So this generic thing is in literature ended up being called as dynamic power management. So essentially, there is some way we are observing tasks arriving. Perhaps we can even predict their arrival, and then or look at the queue, and then based upon that, we are going to be controlling the service provider via some sort of an on and off command. In a simple case, and more generally, you can imagine there could be different degrees of being off. So there are a lot of sleep states, deeper and deeper sleep states. And this thing could be done for individual components. So through the device driver, you may control disks or radios or things like that. and it could also be kind of for the system as a whole. So that's kind of the concept. And as you might imagine, it is useful because many of these things end up, many of our subsystems, or perhaps even the entire system, end up spending a lot of time in states where there is no one who actively needs them. And this is true for interactive systems. It's true for a lot of other systems where they're just not continually utilized. Now, the problem that happens is that the transition between these different states, if we start with a very simple system on-off state, the transition between these things, as we saw last time, is not zero cost. It takes time, it takes energy. If it was zero cost, then policy, which is in a sense sort of, when we say we design a dynamic power manager, we basically are trying to come up with a policy as to when should we issue the on command, when should we issue the off command. So if the transition cost was zero, then the policy is trivial. Whenever the subsystem or the system is not needed, move to the off state, and as soon as it is needed, come out of it. Okay, and that there would not be any impact. The problem, though, is that in reality, these things are not zero, and that's when the policy becomes important. So again, some examples of hard drives and CPUs and stuff like that. Point being that in all of these cases, there is a non-zero transition cost that is associated. So the basic problems then boil down to are there's a cost of restarting. So we have to restore the state, we have to spin up the hard drive, we may have to stabilize the clocks, we may have to synchronize with the network access point and things like that. So that leads to the couple of questions. When to shut down? So you can imagine that somehow magically I knew the future, and in that case I could make an optimum decision about shutdown. In particular, if I knew when the resource would be needed again, then I can take into account the cost of shutting down, cost of coming back up, how much would I have saved if I had stayed up versus how much would I have saved versus how much energy would I spend staying up versus shutting down, and then make a judicious decision. Of course, you cannot do that. So a very common policy which we see for a bit is that of idle time threshold. So there would be some sort of a threshold you can specify, and what the system does is if the resource has been idle for that threshold period of time, then the resource is shut down. Okay. So in a sense, the intuition is that if it has been idle for a certain period, then we are making a prediction that it's going to remain idle for a long time to come. Okay, because and therefore we should shut it down. So typically, this is what you would see in kind of like laptops and stuff like that. That's that 5-minute idle time. Then we are going to shut it down. Do you think it's a good policy? Like, so this kind of a threshold-based thing. What? So deep down, like I said, it is making essentially making the assertion that if you have been idle for some period of time, then you're going to remain idle for a long time to come, long enough time to come for it to be worthwhile. Do you think that's sort of?
Maybe just after the session, I will wake up most of the time, and I will waste.
Right. So let's look at human users. Okay. Do we behave in a way that I'm going to?
So this is used at my work, where if it's been idle long enough, it's assumed that it's nighttime when we're not open anymore, and then it shuts off overnight.
Right. So it works great for long absences, right? I mean, I'm going for lunch or leaving work or stuff like that, right? So that kind of threshold it will work great, but it's not going to be very effective for these large number of cases where we are away for just a short period of time. Okay, I mean, you could imagine that if the cost was low enough, then even there could be these micro sleep kind of episodes that the system can do. So it will probably not work very effectively there. Another approach you can imagine is that instead of waiting for that threshold period of time, because we are wasting, and remember, whatever our threshold is, during that time, I am wasting energy because the system was not being used, but we keep it up. So now you could imagine. Correct. And we'll see shortly how you look at this threshold. Depending upon the system may give you just a single threshold for the whole system, or it may give you different thresholds for different things. Like, for example, it's not at all uncommon that you may have different thresholds for disk and display and kind of rest of the system. So, actually, just jumping ahead, what do you think it will depend on? I mean, how do you decide the threshold? What factors do you take into account? I mean, all our laptops have some threshold like this somewhere. How do you decide the threshold?
Critical is the energy waste during the idle time. If the idle is consuming a lot of power, you might want to consider have a shorter idle.
Okay, fair point. If it consumes a lot of power during idle time, then you should have a shorter time. Okay.
Like your laptop, it has different threshold when you are using battery or you have the power cord plugged in.
Right. But my question is that how do you decide the threshold?
Behavior, depends on the behavior of the application and
What aspects of the behavior? I mean, firstly, yes, application is you, right? You are the user of the laptop.
I think we should set a cost for waking up. Like a possibility of when I sleep down, a wake up comes very soon.
Mm-hmm.
And I should set some cost for this and maybe
Okay.
solve some.
So we'll see shortly how, actually, I mean, I know, like, at least we set it magically, okay? And I mean, in some cases it's partly because we really don't know much about all these things like how much power and stuff like that. We kind of, sometimes it's purely driven by annoyance, right? I mean, I don't want my screen to go black while I'm in the midst of a lecture, right? I mean, something. So there are certainly those kind of issues also come into play. But clearly, kind of finding the good threshold would certainly be an issue, and that threshold may also change over time. Okay, it's usually not necessarily static. Another approach you can imagine is the following: as soon as the system became idle, so it entered. So, as I mentioned earlier, deep down in the OS, there is kind of a so-called idle loop, right? I mean, so basically, there's a queue of tasks, and if there's nothing to do, then we go into this idle loop, okay? And this can be true for the CPU, but it can be true for any other element of the system as well. So you can imagine that as soon as we go into that idle loop, then we basically call a predictor and basically say, okay, how long are we going to remain idle? And that prediction might be based upon all sort of factors that you may take into account, like prior history and things like that. And based upon that, you can make a prediction. How long am I going to be idle? And if the prediction says long enough, then we decide to shut down. A complementary issue comes up during wake up. So again, the issue is wake up takes time. And presumably your goal, so let's set our goal as one where we say that we want to save the most amount of energy, but not impact the performance of the application. So when shall you wake up? Let's say you had perfect knowledge of future. When would you wake up? Wake the system up. Okay, let's be more precise. Let's say the CPU takes 10 milliseconds to wake up. Just 10 milliseconds before the user comes, right? I mean, so I should pre-wake up prior to when, okay, now of course, that assumes, okay, so just as we were discussing, just before the user or the application, just before some new service request will come, you want to kind of wake up, okay? Of course, again, that's not possible for us to know the future in general. In some cases where we know that the task arrives in a very deterministic fashion, of course we know that, but generally speaking we do not. So very common policy then would be things like on demand, okay, which is when the task comes back, then we start waking up, and of course in this particular case the task takes a hit of performance, and that becomes an issue. And the other one is that we somehow have some sort of a prediction strategy, okay? And of course, if the prediction is wrong, then we end up wasting energy. So if the prediction is wrong in the sense that we declare that the task is going to arrive earlier than it does, then we waste energy. And if it's the other way around, that is we predict too far out, then the behavior would be more like on demand. So again, there's going to be some sort of performance power kind of a trade-off that will happen. So as you might imagine, the amount of lost energy or amount of lost energy in the sense that we either ended up spending extra energy or ended up not saving energy we could have would in part depend upon the system characteristics. So let's again kind of look at the system along the following lines. That it's on, off, it has some, it consumes some power in the on state, some power in the off state. There is some transition time going from on to off and transition power, and off to on there is some transition power. So we have kind of a bunch of these metrics. And then let's imagine that we were in the on state and the system went idle. And I have two choices. I can stay put or I can go to the off state. And let's say the idle time was some particular idle time. So now if that idle time is too short, then we are going to have a problem because if we start going to the off state and then immediately come out of it, then what would happen is that we are going to pay the excess penalty corresponding to this transition cost. And besides, since we are kind of looking at an on-demand wake-up kind of situation, so we are also going to have a bit of a performance hit. So one could think in terms of there is some sort of a break-even point where if the idle time is longer than the break-even time, then I should shut down and otherwise not. So you can basically sort of look at energy consumption both ways, staying put versus going through the idle, going to the off state, compare the two, and sort of get an equation for the break-even time. So it intuitively speaking, therefore, you would say that dynamic power management would be kind of useful if the break-even points are such that the average idle times are longer than the break-even times. Okay, if break-even time is too far out, it could happen, for example, if the saving is not much going to the off state, or maybe the transition costs a lot, then in those cases will not kind of generally benefit from that. It turns out that the best deterministic online algorithms, so let me explain these things. Online algorithms refer to those algorithms which act only based upon the history seen thus far. That as they gather more information, they revise the decision based upon that. Okay, so kind of they have access to the system state, they kind of working with that. Deterministic means that it's a fixed policy upfront. Sort of we are making a policy. It turns out that one can show that selecting the policy with threshold is equal to break-even point. Break-even point is a characteristic of the system. The threshold being equal to the break-even point is the best deterministic online algorithm that there could be. So these simple strategies that we have are optimum, at least in that sense.
What are other choices?
Well, so firstly, I could make prediction type strategies. I could have a stochastic way of looking at it. Okay, and then the other one is that at least in terms of what is the best possible, you could imagine that I somehow magically knew the future. Okay, so that would be so real algorithms are always all going to be online, so there is no choice beyond that. But the deterministic part certainly could be relaxed. You could do some sort of a statistical analysis of prior behavior and work based upon that. So deterministic means upfront fixed policy, some fixed parameter. I'm not doing any learning on the fly now. Okay. So and we'll go a little bit deeper into how sort of that works out. But other choices, so predictive type approaches, where based upon perhaps I have for the class of application I have developed some sort of a prediction model, and then based upon this particular run, I'm going to make prediction about it. And in many applications that could be the case. Like for example, take things like sensing applications and things like that, where there is where the nature of the data depends upon the physical world characteristics, and there are correlations in that. So one could make use of that. Good examples are also things like in many cases in signal processing, like for example for speech in the when speech is coded or processed, they often make use of the fact that during silence zones, we really don't need to process something. So these are called, speech is often dealt in terms of talk spurts and silence. And talk spurt and silence could to some extent be predicted because these are not arbitrary signals coming in. So based upon, oftentimes they sort of express some sort of recent history is predictive of sort of the immediate future, and you can kind of hopefully make use of that. So you could have approaches which seek to predict. So now, in some senses, our threshold-based approach, the fixed timeout threshold, the prediction it is making is, if you kind of think about when would it work? So it's basically saying that if I have been idle for more than threshold period of time, then I'm going to remain idle for threshold plus break-even point of time, right? That's the condition under which it is going to be actually saving power. So this is basically saying that, look, I've selected some threshold based upon whatever, some intuition, and we know that we win only if the idle is more than break-even point in time. So if I've selected a fixed time threshold timeout policy, then essentially my claim is that if I have been idle for more than threshold, then I believe with a very high probability that I'm going to remain idle for at least break-even time more. Okay, and whether this holds true for any given user or not, depends and depends on the nature of the application and all. So choice of threshold is crucial. You can show that if you select the threshold to be equal to break-even, then you are no more than 2x worse than the Oracle policy. Oracle policy is an online algorithm refer to the hypothetical best case where somehow you knew the future. Oracle, who knew the future, would select at every point in time the right decision to somehow select the right thing. So one can show, so this threshold equal to break-even is optimum in the sense that it is no more than 2x worse than the ideal Oracle policy. So worst case for this will happen when idle times are exactly 2 break-even point, right? So what's happening is I've selected threshold equal to break-even. So as soon as I enter idle, I stay on for break-even time. Then I go to the off state and only to be woken up because so I just sort of met the break-even requirement. Now, of course, the issue in all these cases is that we are wasting energy during the threshold period, that initial time in which we are staying on, as well as we of course pay penalty in terms of latency, in terms of kind of picking things up. So now you can imagine better techniques. So again, kind of to answer your what are the other options. So for example, we could perhaps be smarter, begin to act a little bit like Oracle, that is, learn the characteristic of my application better, and then perhaps choose the break-even, choose the threshold better. So for example, if you were to be told that the idle time is very long, then what would your policy be? Let's say as soon as you enter into the idle time, you somehow knew that the idle time is going to be very long, much longer than the break-even. What would you do?
Just wait till the next request.
No, you would shut down immediately. You shut down immediately, right? Because there's no point in waiting till the threshold in that case, right? So if I can begin to somehow learn this particular aspect, perhaps based upon the prior behavior of this application, then I could make use of that. So there is nothing which particularly says that threshold has to be just time to the break-even. But if I knew nothing else, and that again goes back to this issue that deterministic policy, that is, I know nothing else about the system other than the system, then I'm going to pick threshold equal to the break-even point. But I can begin to adapt these things. So there are many different ways people have approached these sort of things. So for example, One is what you can do is you can maintain a set of timeouts, kind of almost like do a simulation in parallel conceptually, and the system tries to figure out what is the optimum value of threshold that works for this particular usage scenario. Question?
If you know that your leaving time is going to be short, what should your policy be? Should you wait longer?
So if you knew that your waiting time, your whatever the next task is going to arrive soon enough, then you should actually not even go to sleep in that case, right? So because all you would do is not save any energy, and you're going to incur a latency cost in that case. Okay. Another other type of things that people try, what they do is they again have multiple possible timeout periods, and then conceptually they keep running a simulation of the system as to how it would have behaved under different timeouts, and then do a weighting of them. So essentially these are all approaches that try to discover the optimum threshold for that particular system, and they try to learn it somehow. Okay. Another type of one is you set a timeout policy, and if it turns out that the user wakes you up if too early, then you know that your threshold was set too optimistically, in which case you should increase it, and kind of the other way around. So you do some sort of an adaptation of the threshold. So there are kind of ideas around this concept where you kind of try to learn what the ideal threshold is going to be. Then there are techniques which kind of do a more of a stochastic analysis. So what they do out there is the following: they try to fit the they basically observe the tasks coming in and all, and they try to develop a stochastic model around it. Okay, so what's the arrival process conceptually, and then they develop an optimized policy around it. So conceptually, those of you who have done control theory and all, you can think of it as learning the behavior of the system under control, which includes the arrival of the task, and I'm going to then synthesize, if you may, an controller which is optimal in some sense. So what people do is they usually pick some simple stochastic model, and a lot of people have shown that kind of Markovian models or semi-Markov type models work very well. So they essentially start with that kind of a model, they fit the observations to that model, and then they run an optimization to come up with the optimum policy for that particular model, and then follow that. Okay, so there's kind of plenty of work in that direction. I'm sort of not going to go into these, but basically there is work where if I were to give you the arrival process of the tasks in terms of some distribution, then you can come up with a policy which is optimized for it, and so the strategy becomes let's learn the parameter of that. Now, when it comes to online algorithm, since where my action can solely be based upon what I have observed thus far, so I'm not an oracle, then the metric which is used to look at the optimality of an algorithm, right? So if we were offline algorithms where the entire data trace was given to us, then the way to claim an algorithm is better or worse is to kind of really look at the entire thing. That's not the situation. We don't know the future, so clearly we can never do as well, generally speaking, as an oracle might. So what's a good metric to say that how well we are doing? So the metric which is used is something called competitive ratio. It's a general way to characterize, nothing to do with power management, it's a general way to characterize how good an online algorithm is. So what it does is it compares the cost of an online algorithm with what an oracle would have done with the optimum offline algorithm. And then kind of the idea is that an algorithm is called C competitive if for any input the cost of the online approach is bounded by C times the cost of the optimum offline approach for the same input, and then you kind of look at the worst case over all such C. So we basically say if an online algorithm is optimum, it's basically another way of saying is that its competitive ratio is the smallest. So when I said that for the threshold equal to break-even case, it is no more than 2 times worse than the optimum Oracle policy. Is basically it had a competitive ratio of 2. So it can never be worse than 2 times on any input. It will never be worse than 2 times what the Oracle would have done. Do you think it's a satisfactory measure? Is this competitive ratio a good way of measuring how well a power management scheme is done? So again, the metric it is using is that on no input in this case being the way the tasks were arriving, in no input is it ever going to consume more than 2x the power of what an optimum Oracle algorithm, which obviously cannot be realized in practice, can do. So do you think this is a good measure?
It might it says it might be like 2 times worse, but actual scenario it might be like much better than that.
Yeah, so it's not giving you the average, right? It's giving you the worst case. So the worst case may happen in some peculiar situation, and that's what we're letting it drive by. But theoretically, there aren't very many strong results in terms of being able to say something on the average case, because now it's going to depend upon the distribution. So people are usually these things are quoted in terms of the competitive ratio. So there's a classical result which basically says that the best competitive ratio achieved by any deterministic online algorithm is 2. Again, this has nothing to do with power management. So any best competitive ratio achievable by any deterministic. So in that sense, T threshold equal to T breakeven is an optimum algorithm. Okay, it's the best one can do if breakeven, if a competitive ratio is a measure. Now, if we are somehow given the idle period distribution, okay, so I know I somehow am given that, so now we are going into the stochastic realm, then one can show that exist algorithms whose competitive ratio is around 1 over E minus 1, it is around 1.6. Okay, so in that case we can do better. So knowledge obviously buys us. Okay, so if we knew nothing about it, that is, we're looking at deterministic algorithm, we can do 2x. But if we are given this, then we can do better. Thing in this case tends to be more like, firstly we need to know the distribution, but maybe that is where your prior observations come into play. So stochastic models can do better. The other complication comes is that usually we don't just have 2 states. It's not simply on and off. We are given multiple states. So imagine a system where we have an on state, and then we have many possible off states of deeper and deeper sleep. And by that what I mean is that they will have some power consumption while they are in the sleep state, and there will be some cost of coming out of it. And usually there is a series of these off states. So I can go the lower the power consumption in the sleep state, usually it's costlier to come out of it. Okay, so deeper and deeper sleep means more and more cost to come out of it. So you could model these things in terms of how much energy, how much power consumption, energy dissipation rate is in some particular state I, and how much would it cost to come back to state 0. State 0 is our kind of active state, and there's this single active state. And we can order our states in terms of increasingly deeper sleep, that is, they consume less power, and coming out is relatively cheaper. And when we are in the active state, there is no cost associated. So now you can think of that if the system were to be in any given state, then the energy that it would have consumed over time would basically correspond to the area under a line where the slope of the line corresponds to the power consumption, right? So power integrated with time gives us the energy that is being consumed. So sharper the slope, or more the slope, the more higher power being consumed in that state. So essentially, now you might think of lines that okay, one more thing. And the intercept basically says something about what is the cost, because if I am transitioning into a lower power state, then there's going to be a round trip cost. So I have to pay some additional overhead. So even though in this case, for example, state 4 has the least slope, but it has the highest intercept, so it's going to take a lot to come out. So my good policy is not going to be jump as soon as I'm idle jump to state 4, but rather on the other hand, state 1, which has a sharp slope, but has a very small intercept. So if I'm going to sleep for small periods of time, then that's the good state to go to. So intuitively, then what happens is you can kind of plot all of these things. In some sense, it's saying if my idle time is less than T1, then I'm better off sticking with the slope with state 1. If it is going to be more, then I'll transition out here and transition out here. So in these systems, usually there are multiple thresholds. And as those thresholds are crossed, you go deeper and deeper into the sleep mode. If somehow you knew, again, ability to predict, if somehow you knew that your idle time is going to be very long, then you can immediately jump to that particular optimum state. So, so that's kind of the algorithm. So you basically traverse this lower envelope, and then you have a bunch of thresholds corresponding to different crossover points. Again, one can show that this algorithm is optimum in the same sense of being too competitive, and there is a stochastic version of it, which again is optimum, turns out, based upon the same criteria we discussed earlier. So typical, our real systems tend to be closer to this kind of model, which is multiple states, and you're kind of going deeper and deeper into it. So upshot is you can certainly, if you're shooting for a simple system, you can basically imagine that setting the thresholds corresponding to these points, okay, and which will again, essentially this is kind of the break-even point for single state systems. And if on the other hand you somehow knew the distribution of the task arrival, then you can do better. And not describing that algorithm, but there exists algorithms which can do better in that case. So when it comes time to implement DPM in practice, there are a bunch of questions that one would have to answer. How should we do? What are these states? What happens? So there, when I mentioned there are a bunch of these possible states and all, they basically are implementing shutdown in different ways, and therefore are able to save different amount of energy, but with different amount of cost coming out. So a very common one is clock gating. You basically turn off the clock. That turning off the clock can either happen by kind of just AND gate, you zero it out, to one where you actually shut down the clock source. Supply shutdown, that's kind of obvious. Display shutdown, motor shutdown, all those things. And the other question is, where is it done? This is a discussion we had earlier a few classes back. What's the good place to do this? Of course, user can do it, but you can have application, compiler, OS, firmware, hardware. All of these things kind of have their fingers in this game, and in it, most systems, it's a some complicated mix. It could be some things are done in, like the disk may be handled in hardware or by the disk controller, whereas display may be done by the main seat, by the OS. So it could be some complicated kind of stuff going on. As I mentioned last time around, there is this sort of, at least on Intel architecture type computers, there is a standard called ACPI, which basically provides a way for operating systems to control the platform using some very standardized calls. So ACPI basically is an interface to BIOS. It talks to it via, so board manufacturer kind of implements this, and then the OS kind of works of that. We're going to describe that briefly a little bit later. So ACPI is how sort of a lot of modern power management is implemented. Now that was shutdown. We saw earlier that voltage and speed, that's the other trade-off we have. So one of the things that happened was that starting early 2000s or so, systems where you had the capability to essentially change speed and the voltage of the processor. Potentially other things began to emerge also. So what I described last time in terms of parallelism and things like that and changing the voltage at design time, you could imagine some similar type of stuff, that is voltage versus speed trade-off being done at runtime also. So conceptually the idea is that I have a certain amount of time. I could either do it by running it at the maximum speed, and then during the idle time I shut down using DPM, or alternatively I can run the task at a slower speed and occupy all the available time. So DPM does the left hand side, and what we are talking now is kind of on the right hand side. And as we saw sort of earlier in the course, given your leakage current, leakage energy, leakage power versus sort of active mode power, where they lie in this thing, it will end up affecting which one turns out to be better. So the concept has been around much prior to before it appeared in commercial products. So some of the earliest papers on this thing were around like 93, 94 time frame, where some sort of research chips began to emerge. And the concept, one way these things work is the following. So I have some hardware, a processor. Somehow it exposes a power speed knob. So somehow I can control its voltage and frequency. And then there are tasks arriving for it to be processed. I'm going to look at this task queue. So essentially, if the queue starts getting filled up, I'm going to speed up the processor. If the queue is relatively empty, then I'm going to slow down the processor. And so what they do is they monitor the number of tasks waiting in the queue, filter it so that you kind of smooth it out, you're not kind of susceptible to the short bursts, and then you control this knob. So that's kind of the concept. So another way of looking at it is the following. Let's say I have certain amount of time to do some task. Okay, so that's the time T frame, and imagine that during that T frame, as the tasks are arriving, I have two possible choices. Okay, so one is I just run the task at the max speed and then you remain idle, and the other one is that once the task comes, let's say somehow I knew how long it would have taken at maximum speed, and if it's going to not use the entire T frame, then I'm going to slow down the processor. So on the x-axis, what you are seeing is that what is the normalized workload, which is that if the task had run at the full speed, then what the workload would have been. So for example, if the task was very tiny, would have taken a very short time running at full speed, then the workload is 0. If the task would have occupied entire T frame, then the workload is 1. And as you can imagine, in case of the policy where I run it at the maximum speed, it will follow the red curve. As the task amount grows, then it's going to linearly increase. But now imagine I follow a different policy. What I do is I look at the task, that's the right hand side, I just look at how long the task would have taken if it had run at full speed, and then slow it down so that it will occupy the whole process. So if the task had occupied, let's say, it would occupy half the frame, half the T frame, then I'm going to slow it down by a factor of 2 and correspondingly lower the voltage and save on power. And it turns out that the curve that you would see would look something like the following. Intuitively, it makes sense. If the task needed all the time, even at full speed, then really this right-hand scheme is not going to buy you anything. If on the other hand the task was so tiny, so short, then again I'm not going to benefit much because it would have taken 0 energy anyway. So on the two extremes it matches. It's in the middle where you end up having a gain. Okay, so it's essentially saying that it's better to kind of make use of the entire time budget that you have. Now, this strategy, as you might imagine, is benefiting from that CV square F term. If that term dominates, we're going to look like this. If on the other hand, the leakage term dominates, then this scheme is going to win out because the leakage, in this case, we pay for the leakage energy throughout, whereas on the left case, if we are smart about power management, So, but this right now we sort of in these pictures I'm not taking into account the leakage. So I can do this kind of slow down and occupy the entire frame. Now let's imagine a more complicated system. Let's say at the beginning of every time slot is t frame, a new task comes. It could be an image that you need to process or something like that, and somehow you get to look at the image and say, okay, how long it's going to take. So I can now play the same game of averaging over multiple time slots. So imagine something like the following. Let's say my first frame, I had a task which needed 100% of the frame. And in the second frame, I had a task which needed only a quarter of the frame when running at full speed. So I have two possibilities. One is I can leave the first task as is and slow down just the second task at 4 times. And the other possibility is I can think of it as a task which needs 1.25 frames, and I have 2 frames available. So I'm going to slow both of them down uniformly so that even this task takes somewhat longer. It doesn't finish by this time, and this time occupies this. Okay, so in this case, I'm basically saying, look, let's consider 2 tasks at a time and slow them down. And again, kind of you work on the numbers, you would see that if leakage power is not the dominating issue, then this guy is kind of going to win out. That is, it is better to take blocks of tasks and stretch them out as opposed to single tasks at a time. So in this case, the processor would have run at Fmax for the first frame and some very low frequency in the second frame. Whereas in this bottom case, it's going to have run at some intermediate frequency throughout. Okay, so it's better to run at some intermediate speed throughout as opposed to kind of this burst because thing.
I have a question about what defines the size of the frame?
What
Defines the length of the frame?
imagine a TDMA type system, right? So something like it may be every time the camera is capturing an image or things like that. Okay, so camera is sending me an image every 30 milliseconds. Somehow I get to look at the image. Okay, quick estimate. I'm going to process it now. So if I were to look at blocks of images and process them, I'm better off from an energy perspective. In each case, I'm maintaining the same throughput, right? What am I changing? I'm changing the delay, right? In the first case, I'm guaranteeing that every task is done before the next frame begins. In the second case, I'm relaxing that. In fact, in the worst case, the first task may have a latency which is almost as close to the entire 2 frames worth. Okay, so essentially, kind of the same kind of latency power trade-off. What question?
The second case looks for me as you are doubling the size of the frame. Is that correct?
Second case is essentially as if I'm doubling the size of the frame and taking the 2 tasks together. Okay. Now, the reason this thing works again is because of the convex shape of the curve. This property that I'm better off really is because of the convexity of the curve out here. Okay, there are processors where, for a variety of reasons, the power versus voltage, power versus speed versus power curve may not be convex, in which case these properties do not necessarily hold true. So moral story out of this thing is, number one, it's unless leakage dominates, you're better off making use of the time available to you. And the second thing is, bigger and bigger groups of tasks that you consider at a time, kind of blocks of tasks, the better off you would be in terms of power, even though the sacrifice you're going to make is in terms of latency. So that's basically what's happening. So that's kind of the basic concept behind this what is called as dynamic DVFS, dynamic voltage frequency scaling, which is very distinct from dynamic frequency scaling. Dynamic frequency scaling says I keep the voltage constant, I just lower the frequency. So I may have an Fmax, but I'm willing to operate at a lower speed. It helps with power for sure, but as we saw, it may not, generally doesn't help with energy. whereas DVFS helps with energy as well. Okay, so it's because I'm also, as I'm lowering the frequency, I'm correspondingly also lowering the voltage. Now it's precisely this aspect which also makes things complicated. In DFS, all I have to do is to slow down the clock, and that can be done in a whole bunch of ways, but the rest of the system isn't changed. But in DVFS, I somehow need to change the voltage as well. So I need support for that. So somehow I need some sort of a power supply which is software controllable and is going to generate this voltage. And this is where kind of complication comes. So implied in this story is that for any given voltage, there is an Fmax, or turning it around, for any desired frequency, there's a minimum voltage. Unfortunately, this mapping is something which you cannot just design up front. Okay, I mean, you can do an approximate design, but it will depend upon the specific chip. What I mean by that is I make 10 copies of the chip. Each copy may have a different mapping. So that's problem number one, because there are variations in manufacturing. And the problem number two is it depends upon the ambient condition, as in if I'm operating in a 20-degree temperature versus 30-degree temperature, that curve is going to differ. Okay? And actually the third issue, which is as the chip ages, this mapping is going to change as well. So anytime you have two knobs and which are related by this function which is highly variable, you have a problem. Because how do I learn that? Okay, if I'm writing software for laptop number one and identical laptop number two, they may have different mapping. So one way you can deal with this thing is to have a very conservative table. Okay, somehow you calibrate the hell out of it, put a lot of fudge factors, and you basically come up with a very conservative mapping between voltage and frequency. Conservative means that for any given voltage, I'll have a lower Fmax than what might actually be possible on that system. Okay? The problem, of course, of that is it's very hard to come up with these things, and you'll have a lot of stuff left on the table. So ideally, it would be great if the system gives us a single knob. I basically say run at this speed, and it automatically selects the right voltage for it, right voltage for that specific piece of hardware under that current condition. So what made DVFS realistic was exactly this capability, that you can let the system control the voltage automatically, as opposed to you having to kind of deal with this mapping, which you may get wrong. So one example of something like this was, so one approach for this, which no one uses, but historically is of interest, because it was the very first attempt, which basically said, the problem is coming from having a voltage to frequency mapping. So one way to address this thing is to not have clocks at all. So if I only have voltage and the circuit doesn't need clocks, the problem disappears. And there is a family, there is a way to design circuits which are called self-time circuits. The idea is there's no clock. Every time kind of one stage of hardware will, at the circuit level, wait for the previous stage to produce a result before proceeding. So you no longer operate on clock ticks, but rather you handshake with it every stage. So these are called self-time circuits, popularized quite a bit by like one of the professors at Caltech. A small number of groups in the world who have been fond of this, and they kind of, for a variety of reasons, they kind of have advocated it. Turns out that's a great approach here. So I have some processor. There is an input where the tasks come. We detect how many tasks are waiting. We look at them. Depending upon if this buffer is full or not, we tell we increase the voltage. So it's essentially a control loop. We increase or reduce the voltage, and then the speed changes accordingly. Okay, so essentially a simple control loop running out here. So this works great, except these kind of clockless circuits are not very popular. So the way to do these things with clocked circuit is, so there may be some sort of a synchronous system, is the following. So similar concept again, there's an input buffer. I'm looking at the state of the input buffer. I feed it through some sort of a filter. So all this other stuff could be hardware or software, doesn't matter. Then what we do is, based upon this, we control the rate. So there is some little module to which we basically say this is the speed I need. And what this guy does is it does the following. It basically controls power supply, and that power supply also controls an oscillator, which is the clock frequency. So as we increase the supply, the VDD goes up. This oscillator is on chip, and it has a nice property that it will run at the speed corresponding to this voltage. So this is a voltage controlled oscillator basically. Okay, we increase the voltage, its frequencies go up. If we reduce the voltage, its frequency goes down. So automatically this guy calibrates to this specific piece of hardware under the current conditions. I don't have to do that mapping. So we are setting one parameter, namely the voltage, or think of it like the speed. Voltage gets selected, and the corresponding maximum possible frequency is automatically set. And then this is the feedback out here. And essentially what we do is we look at, compare the error. So we say there's a certain speed I need, there's a certain speed the system is currently running at, I'm going to alter it. So it's a control loop that if I'm not hitting the right speed, I'm going to just increase the frequency accordingly. So this works great because again, I don't have to worry about the mapping. This circuit, since this ring oscillator, since it's sitting on the same chip, so it's subjected to the same characteristics. So if this chip I had was unusually slow for whatever reason, or unusually just had some unusual characteristic, then the same characteristics will also affect this oscillator. Okay, so we kind of benefit. So the mapping happens automatically. Yet another approach is that sometimes what they do is on the same chip, they'll put what are called as canary circuits. So I'm sure you've heard this term, like miners carry canaries into the thing, so that if there is a fire danger or something, they kind of detect that and you react to it. Okay, so canary circuits are circuits put onto the chip whose characteristics are the same as your main processor. So if this processor is slower, then so would that circuit be. And then you kind of look at the delay of that circuit and then set your oscillator speed accordingly. Okay, so if you knew that at the same voltage, this particular processor runs slower, well, you are going to set that max slower. So there are a bunch of different approaches, but you've got to deal with this issue of that voltage to frequency mapping is something that you have to specifically tailor for. So I recall like when this capability of DVFS had first appeared. So back in like late 90s, and I was in a group, we were working on this also. So we had to go through all sort of contortions. That is, we'll maintain a table where we'll have frequency to voltage thing, and we would kind of make sure that across our hardware and all, it will continue working. And there were still instances where we would fail, and you would still have to do things in a very controlled fashion. Like for example, let's say I am lowering the voltage. You have to do things in the right sequence. You have to first lower the frequency, then lower the voltage, because if you did it the other way around, then the system would crash. Because in a transient time, I would have a lower voltage than what the frequency needed. So complications abounded. But by the time this capability got baked into the chips, all these kind of issues came up. So at this stage, you can buy chips and all where DVFS is commonplace. BeagleBone and these kind of things, they all have these kind of capabilities available in principle. Whether we end up using it or not is different. What partly helped was that the voltage supplied to the processor core, that is inside of the rest of the processor, became independent. So there was more control by the chip manufacturers over the clock as well as the voltage. So that's what made DVFS practical, and you find it out of it now. This workload averaging that we talked about, it's not entirely satisfactory in one regard, which is it's good for throughput, but it's obviously messing with deadlines, and in many cases deadlines are critical. There are actually other issues which both DPM and DVFS complicate. So for example, in Intel processors, one of the ways time is maintained is that there is a register which tells you how many clock ticks have happened thus far. Okay, and it's used as a very high resolution timer because it's working at the rate of the core clock of the processor. That works great as long as your processor is not shut down, as well as long as your clock frequency is not changing. So now problems abound with this thing. So let's imagine I have a multi-core chip. One core may be shut down, the other core is up. So the clock ticks they have seen are different. So what started out as synchronized core, after a while they may see different times. Moreover, because of DVFS, the ticks do not necessarily correspond to the time passage. So same n ticks, the corresponding time may depend based upon what the frequency is, and since this DVFS control often happens in hardware, so you don't even have visibility into it. The OS doesn't even get to know about it. So one of the things that they begin to do now is they usually have some part of the chip which is beyond this shutdown and DVFS, so that purely so that it can maintain time accurately. Okay, so because otherwise the time capabilities get messed up. So there are implications on time, there are maintenance of time, there are implications on kind of latency, which one has to worry about. So another kind of work which has happened is to look at ways of scheduling the tasks so that you can meet the deadlines and still do this kind of shutdown or still do DPM and DVFS. So we saw in 202A, 213A that some of the real-time schedulers, so there are methods by which they can be extended so that you can also do shutdown and also do DVFS. The main motivation comes from the following. So even the real-time systems tend to suffer from very low processor utilization. So what I mean by that is, if you were to look at what percentage of time the CPU is occupied, they are usually very low, as low as like 50%, 30% and all. And the reason that could be the case is there may be some tasks which are very tight on deadline, the rest are kind of relatively relaxed. That's one issue. The second issue which comes up is that the entire real-time system work is based around meeting the deadline in the worst case. But average case performance oftentimes, average case utilization is a lot lower. So for example, I may be designing a system where I'm processing images as they're arriving, and I'll design the system so that for the worst case image, it still meets the deadline. But not all images are worst case. So for a lot of data samples, my actual usage of the CPU is a lot less. I finish earlier than the designated deadline. A question then becomes, what should I do? Should I shut down? Should I lower the voltage? All those kind of questions arise. Just to give an example, so some people have shown that if you look at the common embedded benchmarks, embedded system tasks, the ratio of worst case execution time to the best case execution time is oftentimes 10x, 50x, even 100x. Okay, so it's huge. And our entire real-time scheduling work that we saw in previously has been based around worst case execution time. So whereas the reality is somewhere in the middle. So there's a lot of slack in these systems which one could potentially sort of benefit from. The reason this high ratio exists is because sometimes specific data values can be handled by algorithms very easily. There are effects having to do with like floating point operations. They are data dependent. They take less time to multiply zeros, for example, than kind of to arbitrary numbers. So end result is that there is actually a lot of idle opportunities even in deadline-oriented real-time systems. So take an example. So there is, I'm running some sort of a task set on a processor, and so a bunch of periodic tasks. I'm given the period, I'm given the worst case execution time, and I'm given the deadlines. Now, even if I did not, the task always took the worst case execution time, even if I start out with that, there are always opportunities when the processor is idle. So one could certainly make use of that. So in this particular case, CPU utilization, which is worst case execution time divided by the period, it's 84.17%. So looking at this basically says that, you know, I could shut things down and save around 16% of power. Of course, I have to make sure that my wake up is pretty rapid, but let's say somehow I'm able to do it. Maybe I can do it because I learned when the tasks are arriving, and therefore I can pre-wake up. So I could do that. So in this case, 15.83% power savings can be done. If I were to shut down. Now, can I slow the system down? So the question is, could I, instead of doing this shutdown, could I have stretched out every task by this amount of time? Because as we have seen, that will benefit us more. The problem though is then in that case, some of the tasks will miss the deadline because everything is going to be stretched out. So I cannot just stretch things out because in this case, it turns out that you can show task 2 will miss its deadline because if everything is stretched out so that they are uniformly stretched out and kind of fill this gap as opposed to shutting down out here, that will not work. Okay, because you will some higher priority task can miss the deadline. So what is then done is that instead of only shutting down, we selectively slow down the tasks. So it turns out we can decide for every task how much we can slow down, play some magic with the scheduling, and then we kind of decide that what shutdown is possible. So it turns out in this particular case, we do some schedulability analysis. I'm not going to go into it, but we can decide. One approach we can say is, okay, I cannot slow down 15.83%, but can I slow down something smaller? And it turns out we can slow down by roughly 11%. And then I'll still have some idle time. I'll make use of that. And total power savings then, instead of 15% or so, become around 28%. So I gain quite a bit. So I slow down, reduce the voltage, and then whatever is the remaining idle time, I do the shutdown. I can go further. My bottleneck task is task 2, so I leave that at 11% slowdown. But task 1, task 1 is higher priority, I cannot. Task 3, I can slow down even more. So what we begin to do now is that we start walking from our most critical task and always decide, can I slow this down? How much can I slow it down? And sort of walk through all the tasks. Upshot is that if I do things optimally for this particular example, then I can end up with the following scenario. I can slow down task 1 by 11%, task 2 by 11%, task 3 by 90%, and my total power saving is going to be 31.42% or so, ignoring overheads of coming out of changing the voltage and all, and my CPU will be 100% occupied, and all the deadlines will be met. So I guess the moral of the story out here is there are systematic ways one can approach even when deadline is an issue, provided you are able to make use of some of the real-time scheduler kind of process.
What's the visibility of applying this stuff? Is there some real systems do that?
Yeah, it's doable. The part which I'm sort of ignoring out here is there are overheads out here, right? Because every time I change the voltage and frequency, there is a tiny hiccup. Unfortunately, though, that has improved quite a bit. So it used to be that these tiny overheads used to be in like 10 microseconds or something like that. Now you are down to like essentially relatively instantaneous changes. And if you're looking at systems where latencies and all, I mean, most CPU-based systems are probably going to be tens of millisecond type delays and all anyway. So overhead is pretty tiny. So this is easily doable. It's done.
Also, the worst case execution time, I think maybe affected as you should. Sometimes you cannot calculate the worst case execution time very precisely, and there's some hazard.
No, so usually the error is the other direction. That is, worst case execution time is chosen too pessimistically. Okay, whereas your real execution time is going to be much smaller. Okay, so and again, I mean, let's say you are worried about those hazards and all. The way we deal with this thing is by leaving aside some CPU budget for handling those unanticipated delays. You can do the same thing out here. You can say that, look, I'm going to leave aside some of the things to take care of those overloads and all. But usually your problem is another direction. That is, in this case, I'm assuming every task takes its worst case time. In reality, that is not the case. So further, what people do is they actually learn the distribution of the actual execution times. And this again goes back to this issue that many of these tasks are dependent upon something physical. And physical things have correlation that you can observe and learn. So, and therefore recent history becomes some guidance. And if you kind of play with that, you have more to it. So like, for example, if I am processing speech and I encountered that now it is a silence period, you could make use of that fact. Or in some cases, like for example, MPEG video. MPEG video, what happens is your image frames arrive, but the frames are not all identical. There are different types of frames. Some of them carry an entire image worth of information, frame worth of information. Others are just frames which carry some incremental information. They take different amount of time to process. So as soon as the data arises, you can say, aha, this is going to take so much time versus different time. Okay, so even though beforehand you didn't know what a particular task would take and you therefore budgeted for worst case, but once you had a look at it, you could classify it and say, okay, it's going to take shorter time and therefore I can slow down the CPU. So these kind of things are very easily kind of doable, so some amount of prediction and all. So this actually shows some examples. This is the MPEG example I was saying. If you look at the actual execution time, so of the different tasks, there basically are three types of frames. Okay, the one which are coming very rarely, this category, and the smaller one. You don't know beforehand when they're arriving. That depends upon the actual content of the video. But after the frame has arrived, because the decoder has done its job, now when you look at it, you can do. This is an example of a speech coder where essentially while the speech is there, it needs more work. But when there is no speech, when we are in the silence zone, things are less. And again, you can make use of some predictive model as to how long am I going to stay in this particular period and kind of work off that. So you can make use of observation about the data content. Second thing which helps us is that these systems, particularly media type systems, are tolerant to some extent to missed things. So let's say what happens if I mess up and have a wrong prediction about how long, whether the next frame is going to be speech or silence. So what will happen is there will be a tiny one where I'll have some trouble, and then I will recover from that. So a lot of these systems, there is some tolerance to losses, okay, because losses happen elsewhere in the system. So all that's happening is if I mispredict, then there is going to be as if there was a packet loss or something like that. In this case, it's not a packet loss, it's actually a deadline miss. So an occasional deadline miss in return for saving large amount of power often is kind of a good trade-off as well. So people make use of these kind of techniques. So in a sense, exploiting the fact that we can miss some deadlines, exploiting the fact that there is a large dynamic range in actual time that a task needs from one copy to another, and that and then combine it with these ideas of scheduling and all to basically drive the processor into the lowest possible speeds. Okay, so I'm going to skip through some slides, but same example, you kind of do some further games. You can save a lot more power if you were to exploit the actual variation in the tasks as well. Okay, so that was the story on the real-time side. So on real-time systems, also there exists a lot of room for saving power. Now, the showstopper in the story that we have thus far, so we talked about shutdown, we talked about slowdown, we saw that slowing things down can carry a lot of benefits, but the part which we ignored a little bit was leakage. So in reality, slowing down arbitrarily may not be good, because then you are increasing how long you are paying for the leakage. And if leakage was very high, then your better strategy would be to run quickly, shut things down. So in reality, there would be a sweet spot somewhere in the middle. If you're running too fast, then you're missing out on the gains on the dynamic power, the V square term. If you're running too slowly, you're paying the penalty of leakage. So there's going to be some sort of an optimum setting that you can kind of work with. So that's one approach. The other approach is that maybe I can do something about leakage also. Maybe I can mess with it at runtime. So we have seen these slides before, so I'm not going to belabor them, but the main point is, as chips have shrunk, leakage have become a bigger and bigger component of the overall power. So we are in that regime where we cannot simply say slowdown is always good. Okay, there is going to be some there's going to be some intermediate point where things are good. So what that has led to is a further enhancement to this concept of voltage scaling. So it turns out that we can control leakage also. So leakage, if I go back out a slide, leakage depends upon a lot of things, but in particular, leakage also depends upon the threshold voltage that I often mention. So threshold voltage affects the speed of the processor. So if threshold voltage is high, for the same supply voltage, the processor would be slower. But as I lower the threshold voltage, I cause problems in other dimensions. That is, things become more leaky. So threshold voltage, if I could control, I could exercise some control over leakage. So so in particular, as I reduce the threshold voltage, leakage goes up. So if I could play with the threshold voltage, I can control the leakage, and thereby, and I would also affect the dynamic power consumption, and hopefully I can do some sort of an optimization. So what is done in some chips is this notion where I control two knobs now. I control the supply voltage and I control the threshold voltage. And the way you control the threshold voltage is that the bulk silicon, so the chip has the substrate, its voltage you control. So you're controlling the supply voltage and you're controlling the voltage of the underlying substrate. That voltage of the underlying substrate is the one which ends up affecting the threshold. So by changing that, I change the threshold voltage, and of course I change the supply voltage. And I change both of these things together. So this is changing that substrate voltage is called body bias, changing the bias of the entire bulk of the chip. And now, and that changing that then causes the threshold voltage. So this shows something like this. As I'm changing that body bias, I'm changing the threshold voltage. So now what is done, and now we are into the realm where I don't think commercial processors do it, but specialized chips and certainly a lot of research chips have shown this thing to be done. So essentially, you begin to control leakage. I'm going to show this one. Okay. So what's happening out here is that we have supply voltage, we have threshold voltage. We have control over both, and then as we play with this thing, so as supply voltage increases for a given threshold voltage, the performance goes up. For a given voltage, as the threshold, given supply voltage, as the threshold voltage increases, performance goes down, because it's the difference between V and Vt which affects, V minus Vt affects how fast the processor works. So I have control over both. So now I have a two-dimensional adaptation at runtime that I can do. I can control the threshold voltage, I can control the supply voltage, and so what we are seeing out here is the following. If I'm running so this is a processor doing FFT. So FFT is the workload. Okay. For a 10 megahertz curve, it's basically showing what are the possible combinations of threshold voltage and supply voltage as possible. So for 10 megahertz, this is a curve. For 1 megahertz, there is a curve like this, and so on and so forth. So you can see that as at a given threshold voltage, as the frequency goes down, the voltage is going down. Okay, so the dark blue lines correspond to that. For any combination of voltage and threshold voltage, there is going to be some energy there's going to be some energy curve. So these contour curves that you are seeing correspond to iso energy curves. That is basically anywhere on this inner loop, it says 1.1 is basically saying that on this inner loop, at any point wherever I am, I'm going to have a certain amount of energy per operation. So now the game basically becomes that I need a certain performance. So let's say my FFT performance needs 1 megahertz. And then what I'm going to do is I'm going to basically say on this 1 megahertz curve, I could have operated anywhere, but the place I'm going to operate at is where, which is tangent to my least energy contour curve. Okay, so so essentially the tangent points correspond to this. So you can imagine that this dotted red line corresponds to the least energy point of operation possible, because that is where it would be tangent to one of the frequency curves. So essentially, the way these systems operate is you have a certain speed desired, you select that, and based upon that, using conceptually a map like this, you kind of identify what is the threshold voltage and what is the supply voltage, and to achieve a certain threshold voltage, you actually change the body bias. If you ever look at the pinout of chips, their data sheets, they will have VDD, they'll have ground, but they'll usually they'll have a pin for what is called as body bias. Usually we tie the body bias to ground. In these systems, we tie the body bias to another power supply, which we control using software. And by manipulating both of these, we can kind of operate on this dotted red line. And essentially, as my speed requirements change, I can basically traverse the equivalent of this dotted red curve for any given system. So it's easily doable. With the additional cost basically is that you need this additional power supply. But the other issue which I mentioned earlier is, again, now you have another calibration problem. I'm setting the body bias. It is going to result in a certain threshold voltage. What if I'm wrong? If I'm wrong, then I may not achieve the desired speed. So you have so there is additional lower level support which is needed. So these ideas have been demonstrated and all quite a bit, kind of actual chips and all that people have built, but I don't know whether commercially this kind of stuff is used in any extensive chip. These are certainly been demonstrated more at the research level. And that's where pretty much things stand. So you really have these two knobs, threshold voltage via the bias, supply voltage. Together, we can operate the processor at kind of the least energy point, basically, while meeting a certain frequency requirement. So next up, another complication which comes up in kind of real life systems is the following, that kind of a picture that I portrayed thus far is I can change the frequencies arbitrarily, I can change the voltage correspondingly. In reality, there are going to be some discrete steps. So usually processor may offer you a small number of frequency settings where you're kind of going to operate at. So they usually look something like the following, that you have, if I were to plot energy versus frequency, it's not a smooth curve, but rather there's going to be some setting and then you stay at that frequency, so there's going to be stepwise kind of jump, because I cannot change things arbitrarily. And that complicates stuff as well, because some of the assumptions underlying things like our real optimum frequency may actually be in between two frequencies which are actually feasible. So then you have to work things out, that which one do I pick? If I pick a faster frequency, I waste energy. If I pick a slower frequency, I miss the deadline. So then what is done is you figure out part of my program is going to run at a higher speed, part of my program is going to run at a lower speed, and try to work things out what would work the best. Okay. Riding on top of all of this is an additional issue, which is I could certainly I could do these voltage scaling and frequency scaling, but a confounding factor comes up is the fact that there is also heat generated. So if I'm not careful about it, that can have some interesting ramifications. So chips dissipate heat. That heat affects the temperature. That temperature in turn affects the power consumption, and you can enter into kind of a thermal runaway situation where you think you were aiming for some level of power consumption, but because of the thermal dissipation, you do not. So there's an exponential dependence between leakage and temperature. So as temperature goes up, leakage goes up, and therefore if you're not managing things properly, your power sort of begins to go up. So in higher power chips, when we do dynamic voltage frequency scaling, there is also inevitably a thermal element also. And so when you are setting the voltage, it's done together with also taking into account the temperature side of things. So what's done is chips have temperature sensors all over. You basically develop how the chip is thermally behaving. You make a prediction about what the effect of an action is going to be. So for example, if the chip is very hot, it's probably not a wise idea to keep increasing the frequency more, but rather you slack off. The confounding part is that thermal effects are not immediate because there is a thermal inertia in the chip. So chips take time to, let's say the chip is heating up. You realize that, you lower the frequency immediately. It's not as if the temperature will come down immediately. It's going to keep rising for a while before it starts coming down. So you have to look ahead. And then there are, in case of data centers and all, there are also interaction with kind of the cooling system. So what is, again, kind of the more advanced schemes and all, they basically do voltage, frequency, temperature. All of these three things together are controlled, because, and the further pernicious thing is that the temperature affects the power. Okay, so all of that sort of comes up together. Okay, so there's a complicated set of schemes, but I guess the takeaway for our purposes is there is shutdown and there is performance scaling. Whether the performance scaling is done through supply voltage or whether it is done through supply voltage and the body bias, or even more, whether it is done in a thermally aware fashion. Those are kind of, in a way, separate issues, but at a very high level, these are kind of the two schemes I have. We can shut down, we can slow down, and all the ramifications that come with that. Okay, let's see what other ideas we have. So I'm going to skip this. Yeah, some other circuit level stuff which gets used, I'm sort of skipping over. Okay, this is an example of how trivial things can have an impact potentially. So let's imagine that you're sending data from a processor to another processor. What do you think? So firstly, a lot of energy in our systems go into the actual I/O. It's not the inside the systems, but it's actual bits which are being sent over wires. Let's say you were offered two choices. One was you send fewer bits, compress the data. And the other is you encode the data in some intelligent way, but send the same number of bits. Okay, so I'm allowed to mess with the content, and the other side is going to recover with it. So I have two strategies. One is I encode it, but maintain the size, and the other is I somehow compress it, send fewer bits. So I throw gzip or zip or something like that on it. What do you think will help? Or can the former help? Under what settings can changing the content, properly coding the content may help?
I didn't get the question exactly, but coding, when you have
deciding how I represent the information. So I have to send 10 words, but I can obviously map them, I can encode them into bits in whichever way I want, right? I mean, I can, let's say I'm sending 10 integers, I'm still going to send 10 n-bit numbers, but I'm going to encode, instead of doing the binary encoding, I'm allowed to do some other encoding, okay? Yeah, but no one says you have to use ASCII, right? I mean, let's say I'm sending 10 distinct letters. Okay, I could use the ASCII code, but I can remap those bits, right? I mean, same number of bits, I'm still sending the same number of bits, but I just remap them, okay? So it goes back to when is the power consumed. So if you recall, power is consumed when capacitors are charged or discharged, when transitions take place, right? So one way you can save power is to encode things in a way so that there are fewer transitions taking place. Okay, so for example, we have all heard of gray code. Gray code has the advantage that if I'm sending successive values, then only one bit changes, right? That's what gray code is. Where do in our systems we encounter this kind of thing that successive data values are successive binary numbers, and therefore we can get away with gray coding? No, think of a computer, like think in a processor. Is there something, some bus or something in the processor where things just increase by 1, or most of the times increase by 1 or increase by a fixed step? Yeah, so, well, program counter, okay, so like instruction accesses, that's one. Array accesses, that's another one, right? I mean, we basically are traversing through an array. So there's a DMAing operation, that's another possibility, right? So all of these cases are examples where there's a very specific pattern to the data. And if we were to encode these things appropriately, perhaps I can get away with fewer transitions. So that's the concept which drives this, which has driven some of the work, that I don't have to do, I could recode the I/O the way I'm doing the I/O and come out ahead. So let's give you an examples out here. So address buses usually are incremented by 1, sometimes they're incremented by some fixed length 4 or 8 depending upon the data bus size. So one way I could do this thing is to use gray code, okay, as I mentioned. Let's take another possibility. Okay, so again, address buses. So what across the bus there is some sort of a board, and I'm accessing data from it. Okay, and let's imagine that a lot of the times I just access the next data. So instead of sending a new address every time, what if I were to add an additional line called the increment line? And the idea is that I send the base address, and then from that point on, I just tell it increment equal to 0 means the address is what I'm showing on the bus line, and increment equal to 1 is that just use the next address. I'm not going to send you the next address. Okay, so so in this particular case, the recipient essentially internally enhances the increases the address by some pre-agreed strike. Okay, so if I were to be reading an array of integers, then it will just keep increasing the address by 4 every time. So I'm not sending a new address. All I'm doing is int equal to 1, and I'm saving a lot of bit transitions that are happening. So this is called T04. It's used for target addresses, and kind of the idea is for long arrays or long stretches of program, I can essentially approach a zero transition situation. Okay. So that's one. Another coding which is used is called bus invert coding. So what is done in this case is the following. So let's imagine I'm sending a sequence of words. Okay. So and they have been given to the transmitters, sending them out one by one. Now anytime I send a word, I have two possibilities. I can send the word as is, or alternatively, I'm going to send the invert of the word, but then using an extra line, I'm going to tell you that I'm sending you the invert. So, and the strategy then boils down to is every time I have to send a word, I'm going to evaluate what did I send you previously? Am I better off sending you the word as is, or am I better off sending the word by complementing it, and then indicating that I'm complementing it on this other line. So I've increased the number of wires by 1. That wire is also going to switch, so it's going to consume some power. But statistically, by looking at what is happening on these remaining n bits, I may sort of come out ahead, okay, because if let's say a lot of bits were flipping, then by sending the invert of that, I will have far fewer bits flip. So that's the idea behind BI coding, or bus invert coding, and it turns out that you can again save significant amount of I/O power, and since I/O power is a big fraction of system powers now, often dominating because that's where kind of the big capacitances are, so you come out. These ideas have been used at many different layers, but they make most sense when you are doing like communication over a bus or sort of inter-board communication or inter-chip communication on a big board, those kind of settings. There are hybrid versions out here. There are people who have also explored, like they do statistic analysis and all there. But all being driven by the fact that for communication over wires, excuse me, for communication over wires, what matters is the switches that are happening. 0 to 1 transitions are the ones which sort of cause it.
So for example, the T0 code would then require a synchronous communication, whereas without this technique, you can have asynchronous communication.
This is clearly intended for synchronous, right? I mean, every clock tick, I'm doing something else, right? So these typically get used on kind of a synchronous kind of setting. I'm fetching a whole, I'm doing DMAing, or I'm just like the example I'm given, give me the next instruction, give me the next instruction. So I'm reading a whole block of stuff from DRAM or something like that. So that's
like you basically assume that communication will happen pretty much all the time.
Communication is happening for a long enough stretch of time. So I start the communication, I send you the base thing, and then after that I'm just saying, send me next, send me next, send me next. That's all we are doing, right? So I'm not sending you the new address, basically. You could still do asynchronous, right? I mean, you could imagine doing it in asynchronous way, but it won't benefit because if I'm doing asynchronous, then something else would have used that bus. So I'm kind of lost that control. So unless I have a dedicated bus, it won't happen. So usually what happens is that like PCI buses and all, oftentimes there are transactions when I'm accessing a block of data from the other device. That's where this thing shines. So you can save significant amount with these kind of approaches. I mean, there's some kind of data showing that, but point is by combining these things and we can do. There were some experimental processors and all where they applied even between like the DRAM and the processor. These kind of compression ideas. So. Other things which have been happening is that actually I'm going to come to this thing later. So a lot of things which have happened in systems now are one where initial choices were made in sort of a stupid, naive fashion because energy was not in people's mindset. Okay, so they went ahead and other factors like ease of implementation and all kind of growth things and all. So a very common issue which comes up is that oftentimes we are just wasteful in the way we use the hardware. We could have avoided that, but we don't. So a good example out here is the following, that if you look at inside the operating system, what happens when there is nothing to do. We have seen this story before, that doing nothing very well is important, and what happens when there is nothing to do. So think about like what would happen inside an OS. So when we enter an idle loop, what do you think will cause us to come out of idle loop? Interrupt of some form, right? Okay, good. So there are two types of interrupts. One is an external interrupt, like key getting pressed or something. That's one. But there is another source of interrupt also, which is there is timer events. Okay, so some process we have said, wake me up at this time or whatever, these kind of events. So these are timer events and they are usually sitting in a queue. Now, classically, and I'm using Linux as an example, but this was true for all systems. The way they organized is that deep down there is a timer which orchestrates the whole system. So there's a clock running, and that causes what is called as a timer. That causes that's like the system tick, and it's usually set to like 10 millisecond or maybe 1 millisecond or something like that. So that tick is coming, and then the interrupt handler fires, and then it checks whether it is time for it to handle any of the timer events that the software had scheduled. Okay, so deep down, that's what ends up happening. The problem though is that most of the time there isn't much happening there. Okay, my frontmost event may be far out. the earliest time a process has expressed an interest in being woken up is far out. But meanwhile, what's happening is I'm waking up every 1 millisecond, checking that, oh, is it time to do anything, and then going back to sleep. And that negates the whole shutdown mechanism. So my system really cannot go to shutdown, even though my idle time could have been very long, but I'm actually waking up every 1 millisecond or 10 milliseconds within that. So that's an unnecessary activation of hardware. So one way you can eliminate this thing is just be smart about it. While I'm gone into idle, you shut off that tick, arrange for you to be woken up when it's the time for the frontmost event in your event queue. And meanwhile, during that period, you don't have any ticks. So sounds like obvious. I mean, why didn't we do it that way? But wasn't done. So this led to what is called as tickless kernels or so dynamic ticks. So it essentially ended up improving things quite a bit. What it requires is that when you are entering that idle period, you reprogram that timer so that you eliminate the clock ticks, and instead you arrange to be woken up at the next scheduled event time. And this kind of shows that huge gains to be obtained by this. So number of interrupts with ticks 2002 with tickless over some stretch of time. Same number of events being handled though, and average CPU idle residency time, instead of being able to idle just 650 microseconds, you could idle for almost 10 milliseconds, so huge gains. So these are examples where obvious things which were missed in the initial implementations. I mean, this admittedly is a more complicated kind of thing. So that's an example. Another thing which is being done, this is how tick granularity kind of affects power. Okay, the same thing. Another one which is done is the following. So usually in our systems, a lot of processes schedule these timer requests. Let's say sleep for 1 second, sleep for so many seconds, and all. So what ends up happening though is that every time they say sleep for, like someone should sleep for 1 second, somewhere in the OS, a timer is being created which basically says 1 second from now, kind of wake me up. Now the reality is that 1 second is kind of a loose spec. Okay, an application, but certainly would be tolerant of certain amount of error in that. So what is done in both Windows and Mac OS X now is something called timer coalescing. And kind of the idea is that nearby requests we can coalesce together. The OS can coalesce them together because applications have certain elasticity in them. So you group the timers so that instead of timers happening kind of all over a particular period, we move up some of the timers so that we coalesce them. So the advantage out here is in this case, opportunities for sleep are a lot less because I have a lot of fragmented sleep time. Some of them are too tiny perhaps for us to even go to sleep. But by doing this kind of consolidation, I now have a nice, clean, long period in which the CPU can go to sleep really. So this is kind of picture from Apple, which kind of shows what happens in their system. That bunch of applications issuing timer requests is kind of scattered kind of randomly. So the power use kind of looks like this. Whereas when they do the coalescing, essentially you get a lot of idle time. Whereas here there were far fewer opportunities for idling. So this Windows has something similar. They were all introduced within the past 3 or 4 years, mostly because again, power has, these systems are being used on portable devices with power being a big issue. And yes, these things are certainly more complicated. And yes, it's also the case that certain timers you would still prioritize, like your sound system or video playout where quality matters. But most of the time, timers are being issued with relatively, they're not meant to be tight, but the OS was always treating them to be hard or tight. This is another example. So where what is happening is that we are scheduling some stuff. Because this task got scheduled out here, so I have these two kind of idle time, which are kind of fragmented. But what I could instead do is shift this task a little bit. and then have a meaningful sleep opportunity out here. So by messing with when the processor is waking up, I may still maintain my timing, but I just do it in the right way. In this particular case, it turned out that shifting from here to here didn't affect the deadline, but was much friendlier from a shutdown perspective. So again, these are things which sort of initial algorithms and all approaches never took into account. Okay, so I'm going to stop out here. So next time, 3 of you are talking with the papers and submit your 4 sliders on CCNE by noon on Thursday.